download to your desktop, so you don't have to be online to be looking at it. But the good thing about it is it's in Excel. It's like a big Excel table, so it's familiar to, we're used to looking at that. So this is how it looks. Like I said, it's structured as a table. So down the side, it's got individual entries for different tools. And then because this thing is really pretty big and it's kind of tough to look at if you just open the whole thing, we put in some ability to kind of sort and down select. So you can do that by what we call characterization objective. So we kind of lumped them together as to whether they provide information on geology, hydrogeology, or chemistry. You can also sort by unconsolidated media or bedrock, or saturated. And then you can also sort it by, it says data quality here. It's really the data type that I talked about this morning. So quantitative, semi-quantitative, or qualitative. So this is how it works. It's designed to be hot linked. A lot of stuff has kind of information behind it. So someone was presumptuous enough on our team to create the definition of geology. I'm still trying to find out who did that, but obviously it was a geologist. Maybe a little more useful, you can click on the tools and you get background information about every one of those tools. So this screenshot clicked on ground penetrating radar. So we've got a bunch of citations, just provide background, maybe some of the initial applications of the tool, reports of how it was developed and so on. But if you don't want to go to the trouble of reading all those, we have a short description of what the tool is, and then advantages, like where it's good to use that tool, what kind of data you get from it. And then also, just as important, we have limitations. So, where the tool maybe isn't so good and where you should try to not use it. So once you come up with a set of searches, you hit the search button, and if you get a green box in that tool, then it means that tool provides that kind of data. So that's how this is intended to work. So if you're thinking about, kind of folding this into the integrated site characterization process, you're identifying data gaps like I discussed before, setting characterization objectives, and then you can consult this, using these different sortings to, get you a list of things that you might consider at your site. So here's some screenshots of examples of one of these. So you start off, and these are the kind of the pick boxes that you're working with. So for this example, geology was selected. Then down in this box, this is the parameter. They picked lithology. And then this is the matrix. So you can pick all bedrock or unconsolidated. They picked unconsolidated and saturated. And then here we're going to get quantitative. So you click the search button, and then with that set of entry parameters, you get kind of this long list of tools that show up. It's things like surface geophysics, downhole testing, and then a lot of actual sample, media collection methods. You can add more parameters to a search. So if you do one and you got too much back, you can refine it and save them all in the same, Excel file. So the idea is you consult the tools matrix and, do some more research on what you want to use, and then you write that into your work plan and then go out and collect the data. So back to our example that we talked about this morning, the dry cleaner site. If we remember, there was a characterization objective of delineating the lateral and vertical extent using samples at specified intervals for groundwater and soil. And then there was also the evaluation of the soil vapor. So if you were to use the tools table for that situation, so you pick chemistry, contaminant concentration from that box, and so on, you get this list, which is, a pretty long list of the kind of things you, of course, would expect. All of the sample collection methods, some of the screening, the on-site analytical shows up here. So you can see this isn't just profiling tools. We tried to be pretty complete and include lots of different categories of things. So in this case, you would get 21 tools back. What they actually ended up using was soil gas sampling, which we heard about a little bit ago, direct push sampling for soil and groundwater, and actually the soil vapor as well. And then the big thing here was they had a field lab on site. So I know I went through this quickly with a bunch of screenshots, but it's really pretty intuitive to use this. Like I said, you can download it. It has a lot of good background information on it. All right. So then back to the flowchart process. I'm reiterating again the content of the work plan and the need to really be rigorous about making sure you cover these steps. So I'm talking about this again after the tools selection, because obviously you need to write into your work plan what tools you're using, but you also need to think about what kind of data that you're getting. So if you select a tool like an MIHBT and you're not really used to using that, you should think about at the work plan stage how you're going to get the data and what you're going to do with it. If you're satisfied with the field generated kind of information, if you want a bunch of PDF files of the HBT logs, pressure and flow rate, whatever you're going to do with it, you need to kind of think about that ahead of time, because the last thing you want to do is spend thousands of dollars on a characterization program to generate a bunch of logs that you don't know what to do with. So you need to think about that up front. For example, there are ways that you can use what's produced from those logs to put into like a 3D visualization model. That's something we've done on a few of our sites. But you don't want to kind of stumble into that after the fact. You want to think about it to the extent that you can before you go out to the field. The other point there is at fractured rock sites, especially, if you're doing some of the borehole logging that can be done at fractured rock sites, that might be different than the type of data that you're used to dealing with. So you have to think about that as well, because you might need, specialized software, for example, to generate those integrated borehole logs. The other thing that the plan should have, if you're using this dynamic approach to data collection, you need to outline the process for field changes. So if you plan to, you lay out a grid of borings that you're planning to collect, and if you're following our recommendations, you're going to be looking at the data from those borings as you go. You're not going to put in all 40 of them or whatever without looking at any of the results. So you have to establish a process for what do we do if something unexpected happens. If you think you're starting kind of on the periphery where you don't expect much contamination and then suddenly you find DNAPL, who do you have to call? That situation probably isn't something that the field team leader should handle on his or her own. That probably would involve the whole project team. On the other hand, if they have to move, one boring like 3 feet because of a utility, that might be something that the field team leader can handle without, calling the client. So that kind of stuff you can put into the work plan, because you're not going to think of every situation, but you should try to think about the process you're going to follow. In addition to outlining a process for if things go wrong, you should also include a process for just checking in with the team. So if you're generating this real-time data, you should plan for whether it's daily or a couple of times a week or once a week to convene everyone to actually look at the data you've generated. So, data generated to date, so you can decide what to do next. So again, that should also be in the work plan. All right, so moving down the flowchart to the bottom part, this is what we've heard a lot about already. So I'm not going to talk about the details of how you implement the investigation. I'm going to talk a little bit about what you do with the data that you get. So steps 7 and 8, we have these 6, 7, and 8. So implementing the investigation, performing the data analysis and interpretation, and then updating the CSM. Steps 6 and 7 are really kind of done together now. So this is the data generation and data interpretation, because again, you want to be looking at the data as it's being generated, so you can decide if the rest of your characterization program still makes sense, or if you found something that makes you want to change course, maybe do more locations, less locations, use a different tools, and so on. So one thing regarding how you interpret the new data, you want to try to integrate the new data with the old data. So if you're going through this iterative process of updating your CSM, chances are you have to consider some data that was collected some time ago, maybe years or even 15 or 20 years ago. You don't necessarily want to always just disregard all those old results. So you need to determine how you're going to consider those in your CSM. So if you have the longer screen wells and you have groundwater data, maybe those are still useful for building your CSM. Maybe that's not how you would do the investigation now, but it doesn't mean that you're just starting over with kind of the new mobilization where maybe you're using some of the high resolution tools. So you want to figure out how to integrate that all together. And then we always advocate the multiple lines of evidence approach. This goes along with generating lots of data when you're trying to learn about your site. So back to the dry cleaner example. This is a quick visual summary of what they found when they implemented the investigation that I kind of set up this morning. So the red are greater than and the green are less than. And the triangles are groundwater samples, and then the circles are soil borings. So this is an example of one of the vertical profiles of soil data that they got. Going down, in this case, they determined that sampling every 2 feet sort of represented all the transitions in stratigraphy. So that's the interval that they went with. And then it was analyzed with the mobile lab with the split sample. So you probably noticed the split sample didn't agree all that well. So just like we heard with the last talk, you have to, the team had to decide how usable the rest of the data was. Because this was all screening level, really to try to just get a handle on extent, for example, and to look in the source area, they really didn't have to throw anything out because it turned out that this was about the farthest away that they had for the whole investigation. The other thing that you'll notice is, remember the previous conceptual model was built with 5-foot soil samples. So if you had a 5-foot sample, say from 5 to 10 feet, you would be going across a non-detect up to an 11.5. So again, this shows you the kind of the value of higher resolution data. In terms of the groundwater, the old contour is shown in the black, and the new one, based on the new results, is in the red. So one thing that you probably notice immediately is the fact that the plume goes farther down here than they had thought previously. That obviously has implications with all the, if you can see these labels, apartments and houses and whatnot down here. So then we talked about the fact that the remedy wasn't really responding. Hold on to that thought for a minute, but additional data were collected within the source area to try to see what was going on there. Probably the biggest data gap, at least from my opinion about this site, was the soil vapor. So they did a whole bunch of sampling, and there's actually 2 different screening levels here, but the bottom line is only the green symbols are below all the standards. So they had exceedances everywhere, which isn't probably too surprising considering that this is a dry cleaner, with very shallow groundwater. So they ended up doing the 2 vertically discrete zones, like I mentioned, although they're a little bit closer together spatially. And this is an example of semi-quantitative data because it is units of PCE, but it's not a concentration. All right, so poll question. I know it's past 4 o'clock, but I want a little feedback here. When do you update your CSM for a site?
That's good.
All right, good answer. Someone said something. All right. Yesterday, that was my criteria for whether I was going to finish on time or go long. So ideally, I think to me, this is kind of listed in order of preference, right? You want to at least check whether the new data makes sense with what you know about your site. This doesn't mean you have to, produce a new conceptual site model report with every sample you collect, but you at least should be checking to say, all right, is what we just learned consistent with what we thought? Of course, we have other answers that are probably common, but maybe not as favorable. When a technology fails or when you just know it's just flat out wrong. And then the 5-year thing, of course, tied to 5-year reviews. All right, so the last step, updating the CSM. Again, this is where you want to consider the new data with the old data, and you want to think about how you're going to kind of fold it in whatever form your CSM is. If your CSM is like a 3D visualization model, then this is very literal. You want to figure out how you're going to put in the old data and the new data. If it's a report, if it's cross sections and plan view maps or whatever, you want to think about how to fold it all together. Another thing I'll mention, and I have a couple of case studies after the process slides are done. As you get later in the process and your CSM becomes more mature, the data collection objectives or the data gaps are going to be a lot more specific. So at the beginning of a project, you might have a very general data collection objective like we had for the dry cleaner to determine the extent of the plume. You might have a much more specific question as you advance through your CSM and you're doing more targeted data collection. But the point is you're always updating your CSM, even if you're in a remediation phase. So back to the dry cleaner site. Again, I know this is a very simple presentation, but it's something that we can talk about kind of quickly. This is everything on one figure. So the groundwater, the soil, and the soil vapor. The symbology, again, is the green is below standards and the red and the blue are above. So this is kind of putting it all together. That's the old groundwater contour. That was the new one. And in the source area, what they found, probably not surprisingly, is that they didn't really have an understanding of where the whole source was. It turned out that it was deeper in this part of the site, and they hadn't designed their injections to deal with this. So this is an example of Seth talked about during the optimization study, some of the work that he's done that showed the most common cause of underperformance was incorrect CSMs. And this was an example of that, where they just weren't injecting the amendments in the right place. And then, of course, the vapor intrusion question here. This wasn't the only sampling that they did for soil vapor. This was the first step. They went out and did more subslab sampling. They did indoor air sampling and ended up having to put in mitigation systems in a couple of those buildings. But another point about the actual investigation out here, because they were reviewing the data as it was generated and sort of paying attention to where they had done characterization and where they still had, laid out borings, they were actually able to end the characterization program several days early because they had gotten through everything, because there were some of the borings that they had laid out initially turned out to not be necessary because they met their objectives in a shorter amount of time. So that ended up saving money on the characterization program itself, not even considering how much they potentially saved from continuing to operate that remedy that really wasn't working. All right, so that goes through all the ITRC site characterization flowchart and process and kind of how to update the CSM. Now I've got a couple of real world examples where we've gone through this process. So, and I've got a couple of different sort of scales of sites. So we've got like 15 minutes left or so. So this first site is in the Seattle area. It's actually in Tacoma, Washington. It's called the Well 12A site. It's one that my firm has been working on for EPA and for the Army Corps of Engineers for, gosh, close to a decade now. This site, if the name is familiar to any of you, it was the first site in the US where a mass flux, mass discharge performance metric was in the record of decision. So there was a source area remedy that consisted of excavation and in situ thermal and in situ bio, where the goal for that remedy was a 90% reduction in mass discharge. So obviously that's an interim goal. That's not the final goal for the site. That's still MCLs, but that was the goal for operation of this sort of intensive source area remedy. So the starting CSM, thinking back through the integrated site characterization process, we're defining the problem. Like I said, there was a bioremedy that was selected for a big area of this site, along with targeted in situ thermal and actually some excavation. And this is what the CSM, this literally was the CSM when we started. It was a couple of plan view maps. So this is a zoomed in version of the map, and I know you can't see any of the features, but this is the solvent plume. And then zooming out from that, this is the same scale of the plume here. And these little dots on here are all the water supply wells for the city of Tacoma. And the one that was closest to this site, as you probably could guess, is well 12A. So that's how the site got named. The remedy for the site was, like I said, a bioremediation remedy that was going to treat this entire contaminated thickness. So it was a big site. It wasn't all that deep, but the thickness that was being targeted with the bioremedy was 75 feet, and in some cases almost 100 feet thick. So when you're thinking about an injection-based remedy, kind of obviously you're not going to have a single, set of injection wells that are screened 75 feet because you're never going to get uniform treatment. So you're thinking of, well clustered or maybe nested wells with different screens to try to, inject over that interval. So it's a big remedy. So as is becoming more common, I wish we could do this everywhere. We're doing more characterization. So this is post feasibility study. The ROD is already signed. We need to do some characterization before we design everything. So there was some soil borings put in. Importantly, because the mass discharge goal was built into the new, the ROD amendment at this site, we had to figure out how we were going to measure mass discharge and what the mass discharge actually was before we started the remedy. So the idea was, so just for orientation, the source area is all up in here where all these borings and wells are. The mass flux measurement was going to be done with Transect, which is one of the common methods for doing mass discharge, mass flux measurements. So one Transect of borings here and then one here. So when we started putting in these borings, we were doing sampling with depth of soil and groundwater, and actually we were able to do some hydraulic testing of some of these zones as we were going down. So this is just some photos of the different stratigraphies kind of on the way down through one of these vertical profiles. This is kind of hard to see, but if you can see it, TCE in several hundred micrograms per liter. And by the way, I've added these slides in, so if you printed them out from the website, these next 4 to 5 slides aren't in there, but they'll be in a new version if you want to go back to the link. So one thing, if you can see in the green down here, there's a really, really high conductivity value. It's like 3,500 of this one thin little zone here, along with some pretty high concentrations. So as you do with the Transect method, we had the different borings and then the vertically discrete samples. So you draw the polygons. In this case, we used, essentially rectangles. And then you calculate the mass flux in each one of these using the concentration and the flow, and then you add it all up to get the mass discharge. So when we did that, you can see some of the different stratigraphies represented here. We put this into a visualization model. The important point is that most of the mass discharge was coming through 3 of the stratigraphic units, 96%. So what that allowed us to do was really focus the technologies on where we were going to implement them. So this is a plan view of one concept of the remedy. It didn't end up looking exactly like this, but the thermal zone was up here right in the really high concentration area, excavation near surface, And then the rest of this was treated with bioremediation. So this is just depicting like the ROI from individual injection wells. In a cross-section view, it looked like this, where the excavation obviously was near surface. The in situ thermal was kind of in this area. And then bioremediation was a little bit deeper and a little bit down gradient of the source. So the big message here for purposes of this presentation, we greatly refined the understanding of the site with this one event. Now it was not a cheap event. I didn't explicitly say this, but you couldn't use DPT anywhere out here. This had to all be done with sonic drilling because of the lithology. But as I mentioned, what we found is that nearly 95% of the mass discharge was coming through only about 20 feet out of the 75 to 95 foot zone. Because of that, we were able to reduce the target treatment volume. So instead of injecting over 75 feet, we're only injecting over 20 feet now. Again, because the goal is this reduction in mass discharge. So just the savings in the amount of amendment alone was like $1 million. By the time you consider, well installation and having extra injection wells, it was something like a $3 million savings on the remedy, and the cost of the characterization was like a tenth of that. So it's another good example of how the characterization up front can save money over the long term. All right, so the next couple of examples, if you happen to be in the part one, I talked about aspects of these, but I'll cover them quickly here. This site's a lot closer. This is a Commerce Street site in Vermont. This is another one where we came onto the project post-ROD. So the feasibility study had been done, and the ROD selected a kind of a three-tiered remedy. So ISCO for the really high concentration area, which is this red outline here, greater than 50,000 micrograms per liter. Bio for the outside of the red, but inside the green, and then M&A for the rest of it. So just like the last project that I talked about, as a pre-design characterization, we ran through that integrated site characterization process, identified the data gaps, and went out and did an investigation. So the old, quote unquote, old CSM out here was a TCE released into the sandy aquifer. The sandy aquifer was depicted conveniently as 3 10-foot thick sand layers that were labeled, as you might guess, shallow, intermediate, and deep. And then below that was the clay unit. And then this is just a kind of a concept of the remedy. There's a lot of stuff going on with groundwater flow direction here, which is why the plume looks like this. But the concept was aggressive treatment in the ISCO area, and then biobarriers to intercept the plume and the rest of it. So we used a lot of the tools that were talked about earlier today. MIHBT right in that hotspot. We used the Waterloo APS system. We did a lot of depth discrete grab sampling for soil and groundwater, and we had an on-site lab out there. What we found, kind of the most important thing, is that hotspot where ISCO was going to be implemented is not there anymore. So just from the time that the RI was finished and the FS, the analysis was completed, the highest concentration we saw, and even this is with very targeted sampling, was just a little over half that. So the conclusion was that things had attenuated quite a bit. We also saw a lot of conversion to cis DCE over that time period, which hadn't happened before. Kind of the biggest thing that we saw out here is that there were parts of the plume where the TCE just didn't migrate into areas that you would expect it to based on the gradient. What the hydraulic profiling data told us is that there were these tighter zones that were basically preventing it. And we never would have seen this unless until we put all the data, including the hydraulic data, into the 3D model. And then it just shows up beautifully where you can visualize these lower permeability zones that we saw with the hydraulic profiler, and the TCE basically stops right when it gets to it. So it was really fascinating. But the path forward here, kind of the new thing, is that now that this hotspot isn't there, we think everything can be treated with the bioremediation component of the remedy. So that means that there can be kind of a big savings by not doing ISCO out here. All right, so this last site is one that I also talked about parts of during the part 1 workshop. So I'll cover this part of it quickly. This is another case where it's post record of decision and the feasibility study selected in situ treatment. And this is the old conceptual model where there was about a 15-foot thick sand unit underlined by this, very extensive clay unit that kept everything above it. So based on that, we performed an initial design that was essentially a grid and then biobarriers down gradient, like I mentioned before for the other site. So these are just rows of wells that we're using to intercept contamination. You can see all the development out here. It just wasn't feasible to put in, grids of wells throughout here. And the concentrations were low enough down here that it wouldn't have made sense anyway. But before we went out and just burned in a bunch of injection wells, we thought characterization would be a good idea. So this is back, 10 years ago now. We used MIP to just do profiling on where we thought we should complete the well screens. And then that was done in the source area and also down gradient where we were trying to put those biobarriers. What we saw, as you might expect, is concentrations something like 10 times higher than what was observed ever historically at the site, just because we're getting that greater resolution. We're going and sampling specific zones. So as was said before, we didn't try to correlate a MIP response to a specific solvent concentration. We used the MIP to identify zones we needed to go sample, and then we went in with the DPT and sampled those zones. From the hydrogeology perspective, that clay that was thought to be present at like 40 feet was basically not there. It was only there in a couple of locations. And the real underlying unit was like 80 feet rather than 40 or 45 feet. So in contrast to the well 12A site, here we're basically tripling the thickness we had to treat. So it was kind of reverse. But if we wouldn't have seen this during this phase of the project, we would have spent lots of money putting in the remedy that then would have needed to be changed. So I've got 2 slides here that show, oops, sorry about that, some of the results. I'll just use this one for illustration. And so you can see that, the source concentrations actually went down really quickly and went down to below MCLs within like 18 months. Down gradient, when you're using a biobarrier, what you see is the plume sort of detaching from the biobarrier over time. So it looks different when you're analyzing the data. But what I want to show here is down gradient. There was some uncertainty as to where this plume actually ended. So this biobarrier right here, at the time we were building this remedy, everything down gradient of here was artesian. So it really wasn't feasible to go and put in injection wells when the potentiometric surface is like 10 or 15 feet above the ground. So this was all going to be treated by M&A, but we didn't know where the edge of the plume was. So there was kind of a little mini characterization program within the overall project. So this is an example. We had a mature CSM out here. We learned a lot by paying attention to what was happening as we were installing the remedy, but we had this one specific data gap. So this is the example of, you've got a mature CSM, your data gaps and your data collection objectives are much more specific. So here it was, we don't know where the toe of this plume is, kind of down gradient of where we're doing active treatment. So we had the good fortune of being able to use the EPA Region 8 mobile lab. So it went out onto the site and we did the hydraulic profiling using the tools that were already talked about, combined with groundwater sampling. So this is zoomed out from the scale that I just showed you, but these are the points that we profiled. So this is an HPT log flipped on its side. So this is the ground surface. So this is the pressure log. So you look at this and say, it looked like a big pressure drop here, so that would imply it's a more permeable zone. So let's grab some samples from there. This one was really low, and in this case, it was up over 200 micrograms per liter. Here's another example, same thing, it's kind of flipped on its side. Let's grab samples here again where we saw this kind of sudden pressure drops. In one case, hardly anything there. In this case, it was almost 300 micrograms per liter. And this is, in the area that the sort of the previous conceptual model was, it was like 20 micrograms per liter total solvents. So, gosh, I don't know why these aren't showing up. In any case, we were able to define where the end of the plume was with confidence. And ironically, back to what Seth was talking about with the apples and the oranges, the fruit slide, we used the characterization tools to locate where we wanted to put monitoring wells. Because after we did all that HPT profiling, which took like 6 or 7 days, then we knew where we actually should put kind of the down gradient sentinel monitoring wells. So those were installed after that was all done. So here is the resources that I've been hinting at, all the ITRC stuff. Integrated DNAPL site strategy is a little bit of an older document. It's like an overall site management process. This one is designed, it's an ITRC document. The older ones, you go there and you download a PDF and it reads like a report. The newer documents like the DNAPL characterization and the fractured rock, those are online documents. They're more like websites. So there you go and you navigate around to the sections that you're interested in. The ISM document is on the website. ITRC actually just a couple of months ago announced that there's going to be a new team next year focused on updating the ISM guidance, just because it's been used so much more since it came out. They're kind of they're hoping to get a lot more experts involved in doing a comprehensive update to that document. So if anyone's interested, that team membership will open up probably at the end of this year, and then it'll be a year or two effort to update that document. And then there'll be a new document and new training on it. So as a closing thought, back to the concept of how, maybe 15 years ago this would be logged. I mean, I'm not a geologist, but to me that looks like sand. As it turns out, this is showing what the actual hydraulic conductivities of these, of this sand is. And if you can't see it, this varies over 4 orders of magnitude. So this is obviously, a more coarse sand. It's 10 to the minus 2 centimeters per second. There's little thin units in here. This one's 10 to the minus 6. And then there's a couple that are 10 to the minus 4 that you can barely even see. This is the kind of stuff that you can identify with hydraulic profiling. We're not saying that you have to, have this kind of millimeter level of understanding throughout your whole site. But when you see something like this should clue you in that, your flow, your transport is going to be in this zone. These zones that are this low permeability, that's going to be your storage zones. That's where you have to watch for back diffusion. So anyway, this is my last slide just to summarize everything. You want to drive everything with characterization objectives, have a plan for doing things dynamically, and always update your CSM as you go. And that's it.
All right, yes, perfectly on time. So I don't know if there's any questions for Ryan, or some of the other speakers are still here. Jean's still here, David's still here. Anybody? Everybody's ready to go. All right, a couple things. Please, we recycle name tags. You can leave them on the desk, the table out front. Also, your evaluation forms, we'd love to get them. Also out there on the table. I've got the certificates right here, which I will be handing out just over in the corner here in a couple minutes. I gotta shut the webinar down first. But thank you everybody for being here today, and hope to see you at the next one. All right, thanks. Yeah, thank you. That was perfect.
They can kind of hear something.
Yeah, well, we'll find out. I recorded it. We'll see what it sounds like, and we'll see what happens here. Let's see. All right, well, hopefully this worked okay for you guys in New York and New Jersey. We'll find out later. Send me your feedback. Let me know. Because actually, if this microphone through the computer works okay, it'd be great to just use that in the future. Okay, anyway, take care. Bye.